Hello, hello. How are you? All right. All right, too. We're talking about maximum likelihood estimation, right? And last time we looked at this example where we had our observations x distributed as a Gaussian random variable with mean A and variance A. And what did we find? I think I may not even have brought the thing with me. Where did we get the expression? Yes. A hat equal to minus a half plus the square root of 1 over n times the sum of the squared values of x plus a quarter. Was the maximum likelihood estimate, right? And what we showed was that if the number of data points n was very large, that this was asymptotically unbiased, and that the variance asymptotically approached the Cramer-Rao lower bound. So we end up with something that was asymptotically efficient. And in fact, it turns out, in this case, that A hat asymptotically, as n goes off to infinity, is distributed as, well, let's just do this. That in general, oh, I guess no, it's in this case. It turns out that in this case, this is asymptotically distributed with it's a Gaussian distribution with that in the end it's unbiased with this variance, but that the distribution in fact is Gaussian. Okay? And in general, these properties of asymptotic unbiasedness, asymptotic efficiency, and asymptotic normality hold in general for the maximum likelihood estimate? Okay. So, a big question then is, how big should n be in order to be close to these asymptotic properties? Right? We know that if we get lots and lots and lots and lots of data, or maybe even just lots and lots of data, or maybe even just lots of data, that things are going to get pretty good, but how much data is lots of data? Right? And in general, what happens is that this question is hard to answer analytically. If you wanted to do it analytically, you would want to know something about the PDF for the maximum likelihood estimate itself. So instead, what you do is numerical simulation. And so what we're going to do is take the example that we developed in the last class and do just that. So this is generally called Monte Carlo methods. We just do a whole number of different random trials and investigate what happens with the collection of random trials and try to get a sense of statistical quantities such as the sample mean of the estimate over the course of the trials, the sample variance of the estimate over the course of the trials, look at the distribution of the samples that we generate and kind of get an approximate PDF, and there we have some actual an illustration of what happens. Okay, so we'll illustrate the basic idea using our preceding example. Right, where x of n was equal to a plus wn, n running from 1 up to capital N, and n is now going to be a variable that will adjust in the simulation. And w of n is a Gaussian random variable, zero mean with a variance given by the same as the mean of x, a, that is a. Okay. And so what we need to do is to generate a set of random data to investigate what happens. So in the data generation for trial 1, we generate W0 out to Wn as independent random variables. Okay, now how do we do this? So typically, what you do is generate U of n, which has a distribution that's uniform between 0 and 1 using pseudo-random numbers. Right? And the basic idea behind pseudo-random number generation is just to take a very long binary expansion, a randomly selected binary expansion, and as your seed, and then just chop off the front digit to get a next random number and the next random number and a next random number. So that's the basic idea, and so you just interpret the long binary expansion as something lying between 0 and 1, and so that's the standard way to get these kinds of numbers. And then these are transformed to the random x's using the cumulative distribution function for the random variable for x. And so the cumulative distribution function is running, it's starting at 0 at a value of x equal to minus infinity, and it's ending up at a value of 1 at a value of plus infinity. And then we just kind of find out where we are in that random, between 0 and 1. Right? The cumulative distribution function being the probability that the random variable x is less than a particular value. So if we have a CDF running like this, then the places where the variable is more likely to occur are the steeper areas of the curve because the cumulative probability is going up. And so we just map with the inverse mapping and we get back to where we are. Or we get a value of the random variable that reflects the probability. So that's the typical way that it's done. In MATLAB, functions like rand and rand n, and I don't know, these things have changed their names over the years, but I think typically, I think rand you can use with some arguments that in the default is that'll generate a random number between 0 and 1. Rand n by default generates a random number between, or these things help us generate pseudo random numbers with uniform or Gaussian distributions. And then you can scale them and shift them to adjust the mean and the variance and so forth. Okay? So if I have a uniform random number, if I have a Gaussian random number, then I can use MATLAB in a pretty straightforward way to generate it. If I have a random variable with a different distribution, I can utilize take the inverse of the CDF to get back to the random values in those cases with a little bit more effort. And and there are ways also to approximate the generation of correlated random values in certain situations. And so what we do then is from these random numbers that we generate, we form x of n equal to, in our case, a plus w of n, once we have the w's, okay, for this trial. Okay, and then we calculate a hat, and I'll use an index for the trial number, just based as the minus 1/2 plus the square root of 1 over n times the sum of these random x's that we've just generated. We got to what, add a quarter? Okay. And then we repeat for trials 2, 3, etc., up to some number m. All right? And so now we have an estimate a hat 1 drawn from a set of data. We generate a new set of data. We have then a hat 2 from the new set of data, and then so forth until we have a collection of m estimates coming from m different sets of a number, capital N, of these observations. All right? And then having generated these capital M different values, we can estimate something about the statistics of the maximum likelihood estimate for that value of n. Okay, so if we want to estimate the mean, we can just do that by averaging those estimates. Right, just take the sample mean. We can estimate the variance by taking the average of the square difference between the mean and the sample mean. Okay. All right. And we can estimate the PDF using a histogram of the values of all these a hat k's. Right? And by a histogram, what we do is we just set a bunch of bins, and we see how many of the a hats fell into each bin, and just kind of determine the proportion of the values in there, and we vary the width of the bins in dependence on how many of these samples that we have. Okay? All right? And then you can do this for a variety of values of n. And you can compare the achieved or the estimated variance to the Kramer-Rao lower bound. You can see how close to Gaussian the PDF looks, etc. And you can get a feel, in this case, for how big n has to be in order for you to get pretty reasonable results.
Excuse me. How do we calculate the expected value of a k hat?
Oh, this is, sorry, this is, I want the expected value of a hat. There we go, right? All right, so let's do this numerically. I've run a MATLAB script that does this in the case of our example and generated the results. I think we'll see what's in it. And there's a document up on the course website I will display now a document that is also posted up at the course website, although when I was reviewing it on my way over here, I found a typo in it, so I have to go replace the document that's up toward there now that corrects the typo. And I also added an extra plot with it as well. And so I will add that plot to what's available at the course website. Okay, so let me get this. I'll be projecting this thing here on the screen. How's that look, okay? Fairly straight. Okay. All right. Oh, this is like the one day where they don't have where's the marker? You got a pen I could borrow? Thanks. All right. So, like you said, we're gonna generate these values of x randomly, right? This is our estimate for of the value of a, that random variable a. Here are these expressions that we talked about for estimating the variance and so forth. Okay, I'm going to use 50,000 samples, right, for each value of n. So, depending on how much computation time you have, or how easy it is to generate samples, or how much is involved in the work, certainly the more random values, the better off you're going to get with regard to the estimation. And we will investigate what happens for 4 different values of n. All right, so I will take 5. So the idea is we take 5 we take 5 values of x of n, right? x0, x1, x2, x3, x4. Do that once, then generate another 5 values again, then generate another 5 values again, and do that 50,000 times in total. Calculate this quantity and form the histogram. Okay. Then go back, change the value of n to 20, and then we're going to generate 50,000 sets of 20 random values up here. Do all the calculations, etc. Do the same thing for n equal to 150. Do the same thing for n equal to 250. Okay. Now, the Kramer-Rao lower bound that we determined for this estimation scenario is a squared over n times a plus a half. Okay, and that's the theoretical lower limit for the variance as a function of n. And what we know is that as n increases, as n gets bigger and bigger and bigger and bigger, the achieved variance for this estimate here should eventually approach, for a large enough n, it should approach this value. Okay. Now, estimating variances, estimating these second-order quantities is something that is a little bit more problematic than just estimating the first moments. The first moments, generally, you can get pretty close after for a reasonable number. It's a little less sure as to how high you have to go to get a good estimate of the variance. The variance of the estimate of the variance is higher than the variance of the estimate of the mean. Okay, but nonetheless, with this expression, what we expect is that asymptotically, if I multiply this by n and I use a value of a equal to 1, I've got 1 over 3/2, which is 2/3, with an n down in the denominator. This is where the typo is. So I have 2 over 3 times n is the asymptotic variance. So if I multiply the variance that I have by n, I should be close to 2/3, right? Okay. So we can see whether or not we're approaching the theoretical limit by investigating these kinds of things. All right. All right. So we do all this stuff. What do we do? Okay. Okay, so I'm going to do histograms for these 4 estimates, and we're going to investigate the sample variance here by looking at what happens for smaller values of m equal to 1,000 and m equal to 5,000, and a slightly greater number of values of n. All right? Okay, so I don't know if we want to look at the code first. Let me see here. Yeah, let's just go through the code. So here's the MATLAB code. This is also available at the course website. Okay, and I'm exporting some values into a spreadsheet. And I haven't updated the code in a while, so I'm using, gosh, I forget what DDE stands for, something or other like data exchange, device data exchange or something like that. There are new commands they're actually not even quite new. They're a little bit, they've been around for a while, but like XLS read and XLS write, we can, but this works in any case. So I'm just opening up, this just opens up communication with a particular spreadsheet and so forth. I'm setting a value of a equal to 1, all right, for m equal to 1,000 and for m equal to 5,000, we're just going to generate these statistical estimates. Okay, so here I'm doing this for n equal to 5, 10, 15, 20, and 25. We'll just cycle through those, run this code. And for each value of n, we're going to generate capital M values of the estimate. So we generate the random variables. These are Gaussian random variables with a mean of 0 and a variance of a. So rand n generates a Gaussian random variable with variance of 1. So if I scale it by the square root of a, that will then have a variance of a. So rand n, and I give it the dimensions of the vector, where each one of those things is a random variable. So I have an n vector. I just generate all those vectors all at once. Add a to every value. Those are my values of a. We calculate the estimate, the minus 1/2 plus the square root of the sum of those terms. Okay, off we go. Calculate the sample mean, calculate the sample variance, and then I multiply that sample variance by n, okay, and then I write those things out to a table, and then we do the same thing for m equal to 5,000 and write that thing out. Some of these other things are just where in the spreadsheet we're writing the thing out. To do the histograms, the histograms are going to be run for a value of m equal to 50,000, and we're going to run n from 5, 20, 150, and 250. I just basically do the same thing. I just generate all the random values, formulate the estimates in each case, and then I use the hist command of MATLAB to do the histogram. And then I just normalize the thing into a PDF where the histogram is going to be giving probabilities for the bin, and I want to change that over into something that we scale it by the appropriate amount to make it into a PDF. Okay, and then what I do is I look at a Gaussian PDF for the asymptotic variance that would be. So I generate a Gaussian PDF whose variance is equal to that of the Kramer-Rao lower bound for that value of n. And although I label this as PDF true, it's not really the true PDF. It's just the asymptotically true PDF if we've already achieved that at that particular value of n. And then we just plot the two things together. Okay? So that's the basic idea. And if we look at the tables, And I should point out again that we're first going to look at the variance tables. And so basically, when I've scaled this by n, the variances should just basically be 2/3. Okay, if we've achieved the asymptotic, if we've achieved the Kramer-Al lower bound, then the variance should be close to 2/3. All right, we run the numbers, and for m equal to 1,000, this is what we get. Okay, and a, the true value of a is 1. The true variance, or the asymptotic variance for the estimate, is that 0.667. And you can see that, okay, at n equal to 5, our sample estimate here is, with 1,000 samples, right, is short a little bit. You know, it's down 4% from the true value a little bit. The variance is kind of in the ballpark of 0.667. As I increase the number of points to 10 and 15 and 20 and 25, you can see that we're now starting to bounce around the true value of 1. So we're pretty close in terms of the mean. The variance, you know, again, I'm pointing out that the variance is kind of hard to estimate, and so it's going down and up as well. And you can run these trials over and over again and see some different values. But we see that it's not like we're so far off from the 0.667. So we're kind of in the ballpark even for fairly small values of n. Okay, so we're getting kind of close to the efficiency of this maximum likelihood estimate, even with relatively small numbers of samples. Okay. If we do the trial using more samples in the trial, which should improve the quality of these estimates, you know, there's maybe not so much of a substantive difference, except that we're seeing that the mean value, we're still a little bit short of being unbiased, right? So we've got a better estimate of the mean. We're coming up at about 0.99, so we're a little bit short from 1, as compared to seeing this bouncing around that we did here with 1,000. Okay, but it still looks like the estimates are relatively okay. If we look at the distributions of the estimates, and we get plots that look like the following. This is the plot for the histogram when n is equal to 5. Okay, the dashed curve is what we would expect if that asymptotic efficiency is already obtained, right? So there's a variance associated with it, and it's unbiased. And what we see with the histogram is that for this case with 50,000 samples, that we have a bias. The estimated PDF is shifted to the left a little bit, okay? But it's not that far off from Gaussian. Okay, so we have about a Gaussian distribution. And the variance, like we said, is, well, I mean, the variance looks close. It looks like we're just shifted left a little bit. Okay, if we crank up the number of samples in the trial to 20, we have better agreement now between, you know, the bias has been reduced and the variance is about right. And so we're sitting kind of almost on top of this thing. Okay, notice that the scale is changing here. So this is a peak of 1, right? And we're going from 0 out to 3. I'm just plotting the samples out here that were obtained. If I crank the number n up to 20, I'm starting fairly close to 0, 0.2 up to 1.8. I'm plotting over a narrow range. So it looks like, you know, the spread is about the same, but that's just an artifact of the scale and the plots. Because as I increase the value of n, the variance should decrease in my estimates. And we're seeing that decrease in the estimate by having a taller mode and a narrower peak in here. We also have run the results for a value of n equal to 150, and we're starting to see very little difference between what we would expect with asymptotic normality and the bias and so forth, and so things are looking okay here at a value of n equal to 150. All right, and this is a much higher value than what we reported in the tables. The largest n that we looked at there was 25. So with 150 samples, we're doing pretty good with respect to having an efficient estimator, we would think. Okay, and the value, the same sort of thing for n equal to 250. And my comments from before, so if I'm looking at this and I ignore the scales on the plot, it looks like nothing has changed between there, 150 and 250. But be aware that the scale here is from 0.8 to 1.25 on the horizontal axis, 0 to 8 on the vertical axis. And here we're at a slightly wider scale, and this is a little bit shorter. Okay, so some things to keep in mind are, one is, are we getting asymptotically efficient performance out of our estimator? That is this maximum likelihood estimator giving us the best possible unbiased estimate for that number of data points? But also, as I increase the number of data points, the best performance that I can achieve is better than for a smaller number of data points n. So there are two things going on. One is, how good do I want my estimates to be, or how good am I hoping my estimates to be, and whether or not I am getting the best possible estimate for a particular value of n. Those are two different questions, right? What is the performance that I want to achieve, and am I getting the best performance possible for a particular value of n? So I also plotted these histograms all on the same set of axes, right, running from the ones for, so here's n equal to 5, n equal to 20, n equal to 150, and n equal to 250. And you can see that as I'm using a larger number of data points, the spread of these capital M estimates about the mean value gets narrower and narrower and narrower as I use more data points to generate each estimate. Okay, so remember that n is the number of measurements, the number of observations that I use to generate a single estimate of the parameter A, and m is the number of times that I generate an estimate of A. And so we're looking at the spread of those estimates about the mean and comparing it to this normal distribution that we would expect of an efficient estimator. We're doing that in each case, and you can see that the spread is higher as I use a smaller number of data points, and it narrows as I increase the number of data points. Okay? So what value of n should you use? Well, it depends. I mean, it depends on a whole lot of different factors, right? What's my cost to generate it? And both in terms of, if I'm trying to estimate, and we also are assuming, it might be that I'm trying to estimate the parameter that is valid for a short period of time, and then maybe an hour later it's another period of time. And so depending on how, what is the temporal spacing between my observations? So how many observations can I obtain before I expect the situation to change? Maybe I have to take some action based on my observation or based on my estimate. And so I might want to make a quick estimate of what's going on and then take an appropriate action after having made the estimate. And so I may not have a minute or 5 minutes or an hour or whatever amount of time it might be to generate 250 data points. And so there's a variety of, there may be limitations on the performance that I'm able to achieve given the constraints that I have on the observational scenario. So you know, it might be the case that in this situation, what we might say is that, well, we're really asymptotic. We're basically have an efficient estimator by n equal to 150 or n equal to 50 or something like that, but we might not be able to use that many estimates. But this is the basic idea behind evaluating the performance just by running some numerical trials and seeing how things go. All right? Questions on that? Okay, so let's go back and run through another example of what it looks like to do maximum likelihood estimation. So far, we've investigated it just using our good friend, the constant signal embedded in white Gaussian noise. Although we did that modified one. Let's see, he's got that cleared off. So now we're going to go to our other standard example, which is to think of our signal as being a sinusoidal signal embedded in white Gaussian noise. And for the sinusoidal signal, we've got a variety of parameters that we can look at: the amplitude of the signal, the frequency of the signal, and the phase of the signal. And so we're going to run through an example where we try to estimate the phase. We've looked at the amplitude estimation if we knew the frequency. I think we did the frequency estimation earlier too. Those turn out to be simpler quantities to estimate. The phase is a little tougher. All right. All right, so in this scenario, our signal x is a sinusoidal signal at a frequency omega 0 with a phase angle of phi and an amplitude of a, and it's corrupted by white Gaussian noise, Wn. We make the measurements over some number of time points, capital N. Okay, and let's assume A and omega 0 are known, and we wish to estimate phi. Okay, and you can imagine that probably the most practical scenario is where we know there's a sinusoidal signal, and we're trying to estimate amplitude, frequency, and phase all together. It's a more complicated problem, so let's investigate this simpler problem. Okay. Wn, we assume, let's say, is Gaussian, zero mean, variance sigma squared. Okay. IID with the variance known. Okay, so it's a fairly simple version of this problem. Okay, so as is always the case, the basic idea is we're trying to estimate the phase phi from our observations, and what we utilize is what we know about the statistics and how the PDF depends on the parameter. So the PDF of the observation in terms of the parameter phi is our standard Gaussian 2 pi sigma squared to the minus n over 2 power times the exponential of minus 1 over twice sigma squared times the sum over all the observations of x of n minus its mean, which is the sinusoidal signal. A times the cosine plus phi. Right? And you can take this, and so let's go back to square one, and we say, all right, this is the PDF. What do we know about this? Well, if I look at the negative of the second derivative of the log of the likelihood function with respect to the parameter of interest. So I just perform the differentiation, or take the logarithm and do the differentiation. That it's not too hard to show that this is approximately n times a squared over twice sigma squared. Okay? And that tells me that the variance of phi hat I should expect to be greater than or equal to 2 sigma squared over n times a squared. Okay, so I can gauge the performance of any proposed estimator that I have by comparing to this, right, the Kramer-Rao lower bound. And we can ask whether or not we can factor the likelihood function as, or do we want the log likelihood? Oh, I'm forgetting now. This is phi. Is it the likelihood function or the log likelihood function?
The first partial derivative
Of the log likelihood function, right? Okay. Yeah, that makes sense because we get rid of the first term. Take the log likelihood function, take the derivative, blah, 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 blah. That's right. Okay. Okay. All right. Now, this turns out not to be promising. Okay. So then what we might do is to look for a way to utilize sufficient statistics. Okay. Right? If we look at sufficient statistics, the portion of the likelihood function that pertains to phi involves the term, the sum. We look at the sum of this thing, right? You know, the rest of the, this is the only portion of the likelihood function that involves the parameter phi, okay? And so we're looking for how we can express the portion of the PDF that depends on the parameter of interest in terms of a function of the data and factor out a portion that depends on the data alone that we don't need to worry about. Okay, so the component of interest is going to be this. Okay, and this expression we can express as the sum of the x squareds, right, minus twice a times the sum of the x's times cosine, right, plus a squared times the sum of the cosines squared. Okay. And what we can do to get at this term here is I have here the sum of the x squareds minus, I'll expand this as the cosine of omega n times the cosine phi minus the sine of omega n times the sine of phi. And so we'll get minus 2a times the sum of x of n times cosine omega 0 n times the cosine of phi. We'll also get a minus or a plus 2a times the sum of the x's times the sine of omega 0 n times the sine of phi. And then we have the plus a squared times the sum of the cosine squareds. Okay, so in the factorization of the PDF in terms of a g of t of x phi in an h of x term, this will go into the h of x term, and it comes out as a factor because this is in the argument of the exponential function. So we get the exponential of this times the exponential of all this stuff times the exponential of this. And what we see is that the data-dependent part that relates to the parameters will be this term and this term. Okay? So the sufficient statistic here t is going to be t1 of x and t2 of x. I'm going to have a two-dimensional sufficient statistic. Right? T1 is going to be the sum over all the samples of x of n multiplying a cosine, and T2 is going to be the sum of x of n multiplying sines. Okay? Now, what's the meaning of this? Is that, well, if we do that, let's write out the PDF. Right, P of x phi is going to be 2 pi sigma squared to the minus n over 2 times the exponential of minus 1 over twice sigma squared times a squared times the sum of the cosine squared. Okay, minus 2t1 of x, 2a t1 of x times the cosine of omega 0 n plus phi. Oh, cosine phi, sorry. Yeah. Cosine phi minus 2a t2x times the sine, or plus times the sine of phi. Okay. And then that multiplies the exponential of minus 1 over 2 sigma squared times the sum of the x squareds. So this is h of x, and this is g of t of x phi. Right. So what we have is a two-dimensional sufficient statistic. It doesn't seem possible to get that, to reduce that to a single sufficient statistic. And so the question of whether or not we can have a function of the sufficient statistics whose, if the mean is a scalar multiple of phi, and we're able to, and that scalar multiple doesn't depend on phi, then maybe we can, that gives us the opportunity to find a function of the sufficient statistic that's unbiased for the parameter. But we would, if we were going to take that approach, we'd either have to take T1 or T2. Doesn't look like that's going to work out for us anyway. And then we might think that, well, look, you know, working with a single sufficient statistic when there are two of these things here that says that, you know, look, we really need to have that second sufficient to get all the information out of the parameter. It's not likely that that's going to result in something that's going to be an efficient estimator. So we have a little bit of problem with the trying to take a sufficient statistic approach to getting an efficient estimator. All right, so we kind of run through, you know, these ideas to try to go at directly the Kramer the minimum variance unbiased estimator, and it doesn't look like the standard approaches are going to be all that promising. So what we do instead then is to look for the maximum likelihood estimate, right? And we you know, and with all the various properties of the maximum likelihood estimator that we know, so that if there does exist an efficient estimator, it's going to give us one that achieves the Kramer lower bound. We have to examine the issues associated with, you know, asymptotic efficiency and all that. How many data points n is sufficient for us to get there, right? And if we look at this, minimize or maximizing the PDF in this case is equivalent to minimizing, and I'll write this as J of phi. Right, we've got it's a Gaussian density. There's this 2 pi sigma squared to the minus n over 2 factor up front that doesn't change anything. And then we have the exponential function of minus a positive quantity times the sum of the x of n's minus a times cosine omega 0 n plus phi quantity squared. Right? So we measure the x's, we know the value of a, we know the value omega 0, and what we want to do is, given all those values, we want to choose the phase phi that makes this as small as possible, because that will make the e to the minus times this as big as possible and thereby maximize the likelihood function. Okay? All right, now we can expand J okay. Or we take J. So here's J. And we want to minimize this by choice of phi. So we take the derivative of J with respect to phi. And what do we get? We get 2 times the sum of x of n minus a times the cosine of omega 0 n plus phi times the derivative of this thing with respect to phi. So we'll get the derivative of this with respect to phi as the factor out here. That will give us an a times the sine of omega 0 n plus phi times the derivative of this, which is 1. Okay? All right, so for this to be equal to 0, we need the sum of x of n minus a cosine of omega 0 n plus phi times the sine of omega 0 n plus phi to be equal to 0. Right? Or what we want is the sum of x of n times the sine to be equal to a times the sum of the cosine times the sine. Okay, and this expression here this is the same thing as 1/2 of the sine of twice omega 0 n plus twice phi. Right? The double angle, so because the sine of twice theta is equal to twice the cosine of theta times the sine of theta. So if I think of theta as omega 0 n plus phi, I have twice that here. Okay, and what I'm doing is I'm adding these things up over the values of n. And so essentially I'm approximately integrating a sinusoidal function. So as long as the frequency of this sinusoidal function is not equal to 0, then this is going to be fairly close to 0. Right? So this whole right-hand side will be approximately equal to 0 as long as omega 0 is not equal to 0 or it's not equal to pi. Right? If this is equal to if omega 0 is equal to 0, this is just the sine of 2 pi, and I add that thing up. Likewise, if it's equal to pi, I get twice pi, 2 pi n. That's always just equal to the sine of 2 pi. I add it up. But for frequencies other than these points, or well away from those points especially, that I'm just averaging out a sinusoidal oscillation, that's going to be close to equal to close to 0. So for the derivative of this, in order to maximize the PDF, of the likelihood function, we need the sum of the x's times the sine to be equal to 0. Okay? And we'll mark this as phi hat. And to solve for this, we'll use the formula for a sine of a sum. Okay? So that says that the sum of x of n times the sine of omega 0 n times the cosine of phi hat plus the sine, or let's say the cosine of omega 0 n times the sine of phi hat. We want that to be equal to 0. Okay? And so this gives us that we want the sine of phi hat over the cosine of phi hat to be equal to the sum of the x of n's. This is going to be times the sines divided by the sum of the x of n's times the cosines. And we need a minus sign in here too, right? So if we do the cross terms, this cross term gives us this product. That cross term gives us the other product with the minus sign so that it all works out. Okay? So that we want phi hat will be given by the inverse tangent of, or the negative of the inverse tangent of the sum of x times the sine divided by the sum of the x's times the cosine. Right? And here we notice that that maximum likelihood estimate turns out to be a function of the two joint sufficient statistics that we articulated earlier for the PDF. Okay? Okay. Now, we did a little bit of hand waving in there in terms of this being essentially an approximate expression for the maximum likelihood estimate. And it's approximate only in the sense that that term that involved the sum of the signs was equal to 0. But that's going to be close to 0, especially as n gets larger and larger and larger. And so now we have this closed form expression that should give us a value that's close to the maximum likelihood estimate. And then as n gets bigger and bigger and bigger, this should get closer and closer and closer to an efficient estimate. Okay? One final remark that I'll make here is that for transformed parameters, that if theta hat is the MLE for theta, then alpha hat equal to g of theta hat is the MLE for alpha equal to some function of theta. So if I have a transformation of the parameter via a function g into another parameter value, and I have a maximum likelihood estimate for the original parameter, all I have to do is apply the transformation to the maximum likelihood estimate for theta to get the maximum likelihood estimate for the transformed parameter. And that happens regardless of whether this is linear or nonlinear, or whether it's one-to-one, or whether you have different values of theta giving rise to the same value of alpha or whatnot. Oh no, so this is just separate. So yeah, just as a generic case. Okay. So for instance, if x of n is equal to a plus w of n, right? We know that a hat is equal to the sample mean, right? If we estimate if alpha is equal to x squared is the parameter, we want to estimate something proportional to the power, then alpha hat equal to x bar squared is the maximum likelihood estimate for the power. Okay. And this is a situation too where if I have the maximum likelihood estimate for A, so here to get alpha for a particular alpha, either minus A or plus A, it turns out you don't have to worry about whether or not this is a one-to-one function or not. Just you just apply the transformation and you're all set. Okay. All right. Then I think next time we get together, we're going to look at some more issues associated with maximum likelihood estimation. The examples that we've done so far, we've ended up with closed form expressions that we get from the function. We'll talk a little bit about what do we do if we are not able to in a closed form way get the value of the parameter that minimizes the function. So we'll just do a kind of a little mini tour of optimization methods that sometimes get applied. And then I think 2 lectures from now, so that would be next Thursday, we'll take a look at the EM algorithm as something that often gets invoked for some of those situations, and we'll give an example of that. So have a great weekend. I'll see you next Tuesday. Here's your pen.